Organic chemistry is defined as the study of carbon-containing compounds, but is truly the study of electrons and where the electrons go in a chemical reaction. Scientists have always relied on their powers of observation. In the early 19th century, known compounds were classified into two categories: organic, being derived from living things, and inorganic, derived from non-living sources. It was observed that organic compounds demonstrated similar properties. They were difficult to isolate and purify, and upon heating, they decomposed more readily than inorganic compounds. As chemical knowledge progressed, this theory was proven incorrect and a new definition emerged. Organic compounds became defined as those compounds containing carbon atoms, while inorganic compounds generally were defined as those compounds lacking carbon atoms. Remarkably, most organic compounds consist of carbon and a few other elements, namely hydrogen, oxygen, and nitrogen. To understand life, we need to study organic chemistry. So why carbon? Why does carbon form such a wide variety of molecules? It has two properties that make it different from other molecules in the periodic table. The first of those properties is catenation. Catenation is defined as the bonding of atoms of the same element into a series. Carbon forms very strong bonds to other carbons, allowing the formation of long chains and structures. The second property of carbon that makes it the foundation for life is its ability to form four bonds. The ability to form four bonds allows for diverse compounds where there's the potential for branching at each carbon in the chain. Carbon forms stable double and triple bonds with other carbon atoms and with oxygen and nitrogen atoms. So you can have a variety of bonding configurations for carbon. So carbon works so well, why not silicon? Silicon is below carbon on the periodic table. It is in the same group and can also form four bonds. The answer to this lies in the stability of those bonds. Carbon forms strong bonds with a number of atoms, while silicon does not. So if you look here, you can see that the strength of a carbon-carbon single bond is 339 kilojoules per mole, whereas a silicon bond is 223 kilojoules per mole. So as your textbook states, bond strength goes a long way in forming stable molecules. This last slide shows an example of the different bonding configurations that a carbon can achieve. So the first picture depicts a linear chain of carbons bonded together, and you can see carbon has four potential bonding sites. This second picture is depicting the presence of multiple bonds. When we have two bonds, that is known as a double bond or a pi bond. And when we have three lines, that is known as a triple bond. Here you can see an example of branching, where you have a linear chain of carbons, and then you have various carbons coming off at different branch points. Now you can see why carbon is the foundation of life, because here if you look at oxygen, which can only form two bonds, you're limited in the bonding configuration that you can achieve. So here you only have a linear chain of oxygens, whereas with a carbon you can achieve much more complexity in your structures.